Good day, everyone. I'm Vijay Gupta, and I'll be teaching you this course on fluid mechanics and its application. This is a very practical course in which I would do very little mathematics per se, and mostly I would be doing applications. The mathematics related to this course can be picked up from a book by the same title by Dr. Santosh Gupta and me. The learning objective of this first lecture, in which we'll discuss fluids and properties, is to talk about the principal concerns of the subject of fluid mechanics, the distinguished properties of fluids, and the Newton law of viscosity. Most of this you would have covered in your high school. There are two concerns of the subject of fluid mechanics. First is a fluid applies forces on objects when it moves past them. Conversely, we need to apply a force to move an object through a fluid. The subject of fluid mechanics is largely concerned with calculating these forces. The second concern of the fluid mechanics is that the fluid motion modifies the rate of transfer of heat and vapor from a surface. And this rate of transfer of heat and vapor is required for designing heat transfer equipment and the diffusion equipment, largely engineering concern. So, we need to study how the fluid motion modifies those rates of transfer. This is what we are going to do in this subject. But first, let us talk about the various kinds of forces in the fluid. All of you know that a fluid exerts buoyancy forces on objects which are submerged or partially submerged in it. A boat, a paper boat, floats on water because its weight is being balanced by the vertical force of buoyancy that it experiences. You had learned in your high school that this buoyancy force was first studied by the Greek scientist Archimedes. Then there is a force normal to a surface which is termed as pressure. Pressure is an abiding concern of fluid mechanics and we'll deal with throughout this course. The developing steam in a kettle applies a force which, if not permitted to release, would burst the kettle. We will see various applications of this force of pressure. One of the application of this pressure is shown in this sketch of a basic hydraulic system for a car. This here is the wheel of a car, which is in which there is this pad. There is a hydraulic fluid in this cylinder, and as we press the brake pedal, the fluid goes and presses this cylinder against this, causing friction to apply a torque on the wheel to make it stop. This is the basic mechanism of the hydraulic brakes of a car. Then the other force, the drag force, opposes the motion. If you run against the wind, you experience a force that tends to stop you. This is the force with every moving vehicle experiences. And we have to expend energy to overcome this drag force. These boats, paper boats floating down the river, are they floating with the speed of the boat, with the water, with the stream? If there was a difference in the speed of the flowing water and the boat, a drag force would result, which would either accelerate or decelerate the boat till there is no relative motion between the water and the boat. One positive application of this drag force is in the parachutes. This payload is being delivered from this parachute. The payload in this case is a space capsule. Is being delivered by the parachutes. The parachutes, while coming down, move against the air, and the air applies a force on these parachutes in the upward direction, thus decelerating the downward velocity of the payload. On the other hand, the force that is relative to normal velocity is called a lift. The Australian bowler Michael Stark here is bowling his fast-paced ball as swinger. The ball, if it was going straight, would have followed the red line, but because of outswing, it moves in the direction of the yellow arrow. This arrow an outswing ball. How is it possible? This is possible only if there is a force on the ball in that direction. A direction normal to the direction of motion of the ball. We would later on in this course explain how that side force comes in on the ball. This ball that is shown is moving in that direction. There is a force of air, drag force, which is trying to decelerate it. And there is a side force that results because of the inclined seam. And this side force results in an outswing. The lift is also responsible to keep an airplane flying in the air. It is the lift generated by the relative motion of the airplane with respect to surrounding air that exerts a vertical force on the wing, normal to the direction of motion of the aircraft. And this lift, which is upwards, balances the weight of the aeroplane. We will see later on that this is the result of these vortices that develop in the flow, and they are moving down, and while they are moving down, that means there is a force that is applied on the air downwards, and the reaction to these forces is the force which is applied vertically upwards on the aircraft. Air moving down, and so there is the lift is also responsible for propelling a boat forward. The direction of wind is shown here. The direction of wind, the sail on the boat is so arranged so that the wind comes tangentially onto the sail. Because of the sail, because of the wind flowing over the sail, there is a lift force on the sail. Lift force is perpendicular to the direction of the wind, and a drag force in the direction of the wind itself. The resultant of these two forces is this. By law of parallelogram of forces, we break this force up, the resultant force up, into two components. One, as shown here, in the forward direction, which we have termed here the propulsive thrust, and the other perpendicular to the direction of motion, which we call the side force. We have to overcome this side force, and if we can overcome the side force, the boat would move in the forward direction quite a bit into the wind itself. Here we are showing what generates the side force. The keel of the boat, the portion of the boat below the waterline. As the wind applies a sideways force on the boat tends to move in that direction, causing a relative force, and so the water applies a drag on this force. Since water is much more dense, this force is a large force. So with very small velocity, we can overcome this side force, and so the boat drifts to the side only slightly. Most of the motion is forward. Large area of the keel results in large drag even at a small relative speed. One of the most interesting thing is that we can get oscillating forces even when the winds are steady. Perhaps one of the most famous example is what happened to a bridge at Tacoma Narrows in the Washington state of USA in 1940. This is an actual picture from that. When the bridge was relatively new, only a few months old, there was this windstorm at a very moderate speed of 70 kilometers per hour. And you can see the deck of the wind started oscillating. This oscillation can result only if there is an oscillating force acting on the deck. Unfortunately, the frequency of these oscillations coincided with the natural frequency of the bridge deck, and the bridge collapsed. The bridge was replaced by a new bridge later on. Note that the bridge has been made much stiffer so that the natural frequency is much higher and the wind would not set it up into resonant oscillations. So a problem for wind engineer, aerodynamicist, or a fluid mechanist is to calculate what is the frequency caused by the winds blowing over the deck, and then design a bridge at a frequency much, or with a natural frequency much higher than that frequency. Another example of oscillating forces is what happens in our vocal cords. The air from the lungs is pushed through a narrow opening in our larynx, and though we push the air at a uniform speed, this larynx start vibrating up and down as shown. This is taken with a strobe light so that vocal cord vibration is slowed down. Swimming is again the play of forces between fluid mechanics and bodies. The head, as it goes down, produces a drag, normal and opposed to direction of motion of the hand which is coming down. And this drag force can be broken up into two components. A component in the forward direction, which gives you the thrust, which gives you the force because of which the swimmer accelerates forward, and a lift which keeps him afloat. There is some new research into motility of sperms. The sperms cannot swim like a swimmer does because the size of the sperm is very small. We would learn later on in the course that the forces or the relative magnitude of forces depends upon a parameter called the Reynolds number, which depends upon the size of the object and the speed. The speed of a sperm and the size of the sperm are very small, of the order 50 micrometers, the size of the head of a human sperm, and the speed about 20 micrometer per second. So with those speeds, the viscous forces are very large, and at those large viscous forces, we can see that nothing can move the way a human swimmer moves. This motion is quite different. Next, we will discuss a couple of applications where the motion of the fluid results in modifying the transfer rates. In this picture is shown in the left is shown the chimney at a nuclear power plant. What is the chimney doing in a nuclear power plant? How does a nuclear power plant works? Nuclear power plant works by generating heat in the nuclear core by nuclear reaction. That heat heats up a fluid, usually or quite often a molten metal. This molten metal is taken to a reactor where water is boiled and the water runs a turbine, a steam turbine. This water needs to be recirculated. This water is too hot, so before it goes back to the boiler, it needs to be cooled. That cooling is done in this chimney that is shown here. The hot water is passed through the tubes shown here and here. Is lifted up through this chimney. And this moving air sets up convection across the tubes through which the hot water flows, thereby cooling it. What should be the diameter of the tubes? How many tubes should be there? What should be the height of this chimney? Are all questions for a fluid dynamicist to answer. This picture shows the efficacy of a face mask. The transmission of coronavirus is largely via aerosols or small droplets created by breathing, sneezing, or coughing. The reach of the exhaled air can be effectively reduced using a face mask. Schlieren imaging technique is applied to visualize the airflow caused by a person breathing and coughing. What is a fluid? A fluid is something that flows. What does flowing mean? Let's take this example. There are two flat plates shown hatched, on between which there is a green substance. The lower plate is fixed. On the upper plate, we apply a force F1. If the green substance was a solid, then the upper plate would move under the action of force and will come to a stop after a while when the green substance now has been shown in a brown color, and there is the angle from 90 degrees has reduced to an angle theta 1 less than 90 degrees. What does it mean that there is no more motion of the upper plate when the force F1 is applied? That force F1 must have been overcome by some internal force produced in the solid. This internal force is the shear force. If we applied more force, a larger force F2, then the plate will again come to rest but with more distortion. Now the angle will reduce to theta 2. That means when we deform a solid in shear, a force builds up to oppose the deformation, and that force depends upon the deformation. More the deformation, the more is the force. In earlier case, the opposing force was F1. Now the opposing force is F2 with more deformation. So more the deformation, more is the opposing force. Now, if the substance, the green substance, was not a solid but a fluid, I marked two lines. When you apply a force F, the upper plate never stops. It keeps on moving. And ultimately, it accelerates first, but ultimately it acquires a velocity v. What does that mean? The upper plate keeps moving and the fluid keeps on deforming. No equilibrium state, but an equilibrium velocity v of the plate. The equilibrium velocity v increases as the shear force F increases. This means that mere deformation of fluid does not build up resisting forces. Since there is an equilibrium velocity, more the velocity, larger the force, a resisting force is developing for sure. The resisting force is thus dependent not on deformation but on the rate of deformation. A fluid does not resist shear force by acquiring an equilibrium strain. We define a fluid as a fluid deforms continually under the action of a shear force, but at a rate determined by the magnitude of the shear force and the fluid properties. A fluid at rest or in uniform motion, when there is no deformation, cannot sustain any shear force. This we use as the defining statement of a fluid, as a definition of a fluid. A fluid at rest or uniform motion cannot sustain any shear force. A relative motion of fluid is necessary to develop any shear force. When a fluid is in motion, there may exist shear forces as well. Let us consider the rate of deformation. Again, we have the same setup as before. We have a green fluid. On the green fluid, we have marked two lines at right angle to each other. One a horizontal line segment and one a vertical line segment. This fluid is moving. You would know later on we will do that the fluid have a property with which we say that there is no slip between fluid and the nearby wall. So fluid at the stationary plate would have zero velocity, would be stationary, and fluid adjacent to the moving plate would be moving with the velocity v naught, the velocity of the plate itself. And the higher we go, more is the velocity, lower the velocity is lower. So after a time delta t, upper end of the vertical line moves through a larger distance than does the lower end of the vertical line. So that the location of those two black lines would now be this. So the angle between these two lines have now decreased. What is the decrease in this angle? This decrease is gamma, called the shear deformation, and you would see by simple Taylor series expansion that this would be given by delta Vx over delta y into delta y dt. So this is the additional distance that the upper end of the vertical line has moved over the distance moved by the lower end of the vertical line. So the angle gamma, which is the deformation in delta time delta t, is delta Vx by delta y into delta t angle. The additional deformation divided by delta y would give you this. And then since this is the deformation delta t time, so in unit time or the rate of deformation is delta Vx by delta y. There is a famous law of viscosity, the Newton law of viscosity, which you must have done in your high school, which states the shear stresses in fluids are proportional to rates of shear strain. The rates of shear strain, not the shear strain itself, but the rates of shear strain. So that tau is proportional to gamma dot, the dot representing the differentiation with respect to time, delta gamma by delta t. And we just shown that gamma dot, the rate of deformation, shear deformation, the rate of shear strain is dVx by dy in the case discussed. So for the parallel plate geometry shown earlier, tau, the shear stress, is proportional to delta Vx by delta y. Or introducing the proportionality constant mu, tau is equal to mu delta Vx by delta y. The proportionality constant is termed as the viscosity and is the material property. Now this is a very famous relation, but the applicability of this is not universal. In fact, there are whole classes of fluids which do not obey this law. So The fluids that obey this law are called Newtonian fluids. Newtonian fluids are those fluids which obey the Newton law of viscosity with a constant mu. On the other hand, the fluids which do not obey this law are termed non-Newtonian fluids. We can look at the dimensions of viscosity. Since tau is equal to mu dVx by dy, so dimension of viscosity would be dimension of shear stress divided by dimension of V by y. The dimension of viscosity are force divided by L square, and we get the dimension of mu in MLT system as M L minus 1 T minus 1. The units are correspondingly kilogram per meter second, which also is Pascal second, which is derived from this. This is second and FL minus 2 is Pascal. So Pascal second. The other unit is a poise. Poise is a unit which is equal to 10 raised to minus 1, 0.1 Pascal second. A most commonly used units in fluid mechanics is the centipoise, which is 1/100th of a poise, which is equal to 10 raised to minus 3 or millipascal second. And why is that used? Because viscosity of water at room temperature is about 1 centipoise. Something easy to remember. And centipoise is 10 raised to minus 3 Pascal second. Pascal second is the SI unit which you would be using in all your problems that you do in a course in fluid mechanics. But quite a bit of engineering literature, the viscosity is given in centipoise. There is a wide variation of the viscosity of air. Has a viscosity of 0.0185 centipoise. For gasoline, it is 0.29 centipoise. For water, as we just said, is 1 centipoise. Mercury is a little more viscous, 1.55 centipoise. And the SAE 30 motor oil that you use in your cars typically is 440 times the viscosity of water. 440 centipoise. Very viscous. Glycerine is also a very viscous substance. Effect of viscosity. What does viscosity do? Again, we have similar geometry, two parallel plates with a fluid in between. But in this case, we have the upper plate stationary, just for the convenience of my drawing, that's all. And the lower plate is suddenly start moving at a velocity v naught. Initially, this was all stationary, so the whole fluid was stationary. At time t is equal to 0, the lower plate is set into motion with the impulsive velocity of v naught, suddenly given a velocity v naught. So what will happen? Because of the no slip condition that I discussed just a little while ago, the fluid in the immediate contact with the lower plate starts moving immediately with the velocity v. The fluid adjacent to it is still stationary, so this gives a velocity gradient, which is negative, of course, the velocity decreasing in the upward direction. And so that creates a shear stress. Because of shear stress, the fluid adjacent to this adjacent fluid starts moving slightly. And after a little time, you might give a velocity profile which looks like this. This reddish line shows you the variation of velocity in the vertical direction across the fluid after a little time delta t. a time after the lower plate has set into motion. You see, after a few units, the fluids in the upper layers has not moved at all, has not started moving at this time. Now this has set the velocity gradient again, so there would be more shear stresses, and because of which the effect of the lower motion will penetrate upwards, and we will, after a little more time, we might get a velocity profile like this, and then like this, and then like this. After a long time, we would get a velocity profile which would be straight. We will later on in the course that mathematically we will obtain a straight line profile between the plate. This is the profile that you used in your high school between two parallel plates. You call this flow a Couette flow, a steady state flow after a long time. What is happening? The effect of the motion of the lower plate is diffusing upward. Diffusion is the word. We say the momentum. Later on we'll use another word, vorticity, is diffusing upwards. Penetration and the effect of motion of the bottom plate due to action of viscosity penetrates upwards. This is the effect of viscosity. The penetration increases with time. Action of viscosity is like a process of diffusion. The viscous action of the fluid resists the motion of the lower plate. At this steady state, the fluid attempts to drag the upper plate to the right. There would be shear stress on the lower plate in that direction. This would tend, so we'll need to apply a force constantly on the lower plate to keep it moving. Not only this fluid would apply a shear force in that direction on the upper plate. So we'll need to apply a force on the upper plate in the opposite direction to keep it stationary, to overcome this effect of drag on the upper plate. We'll have occasion to calculate these forces and discuss more later on in the course. A rudimentary viscometer. How do we measure viscosity? We have two drums, an inner drum and an outer drum, or cups. This is, I'm showing the top view of the two cups. There's a fluid in between the two cups. The inner cup is rotating. Because of the viscous action, there would be a force that would develop on the inner cup which we'll need to apply to keep it moving, or a force that we need to apply on the outer cup to keep it from rotating. We measure that force. The picture between the two cylinders, two cups, look like this. The velocity there is omega r. The gap d, the velocity on the stationary cup, is 0. You can know the velocity gradient. So we assume linear velocity in the inner cup. We calculate the velocity gradient. From velocity gradient, we find out the shear stress by applying the Newton's law. Then we find a force on a small element like this. We find a torque of this small element by multiplying by r, the radius, and then integrate to find out the total torque that we need to apply to keep the outer cup from moving. We can measure this and relate it to mu. And that is how the viscosity is calculated using this rudimentary viscometer. We will do this problem later on in the course. I have included here just to give you a flavor of what kind of calculations are moved. Probably you have done this problem in your high school as well. Classification of fluids based on stress-strain relationship. You see, in a solid, there is no rate of strain, just strain, and we have a shear force. For an ideal fluid, non-viscous, if viscosity is 0, we can have any shear rate of strain and there will be no shear stress. For a fluid that we discussed, a Newtonian fluid, there is a linear relationship. Mu is constant, shear stress is mu times rate of strain. But there are other kinds of fluids. A pseudoplastic or a dilettante in which this is not a straight line. These are all not Newtonian fluids. Or we may have a plastic in which up to a given level of shear stress there is no rate of shear strain, but then you can develop any rate of shear strain after that for the same stress. We have fluids that have a threshold, and beyond that you need more shear stress to get a rate of strain. These are known as Bingham plastics. In this course, we would largely, or we would essentially discuss Newtonian fluids only, though within this lecture I'll give you some examples of Bingham plastics. You see, a rod is rotating in a fluid. You can see these two pictures. These are GIFs. The fluid is rising up the rod, and when a big bulb is formed, it collapses down and starts climbing again. In a Newtonian fluid, inertia would dominate and the fluid would move to the edge of the container away from the rod. Centrifugal action. But however, the elastic force generated by the rotation of the rod and the consequent stretches of the polymer chains in the solution that we are using here results in a positive normal force upward. The fluid rises up the rod. The bulbous shape remaining at the end of the video is more onset of instability as the mass that has been forced up the rod relaxes and overcomes the force pushing it from below. The rod climbing effect. Another non-Newtonian effect is the die swell. You see, if the Newtonian fluid was flowing down a die, flowing down a hole, it would follow a contour like this. It will accelerate, and because of acceleration, the cross section will decrease because volume flow rate at any two cross sections is the same. So if the fluid is accelerating downwards, then downwards the cross sectional area would have been small. But you use polymers like a 2% aqueous solution of polyacrylamide. The fluid swells after coming. Fluid swells means its velocity is decreased because of being pulled up by a normal force. There is a third non-Newtonian effect that I want to show you, and this is very interesting. An open siphon. Again, this is because of this. Polyethylene oxide, 5.5% solution of polyethylene oxide, a polymer. You start the flow, and because of tension, because in this, the fluid, the the beaker empties itself. That brings us to the end of this lecture. In the next presentation, we'll discuss fluid flow phenomena. Thank you.